Most developers kill their systems by choosing vertical scaling when they actually need horizontal distribution. You assume a bigger machine solves your bottleneck, but you are just waiting for a catastrophic crash. Today, we master the architecture of infinite growth. Is your website struggling under a sudden surge in traffic? You start with a single server, which has a fixed capacity defined by its hardware limits. You might try to fix this by upgrading that server to be more powerful. But why add more power if one just gets bigger? Eventually, that single machine will reach its limit and crash completely. Instead, you can use multiple nodes, which are individual servers working together. By spreading the load across several nodes, your total capacity becomes the number of nodes multiplied by the capacity of each one. Think of this like choosing between building one massive skyscraper, which we call vertical scaling, or building a neighborhood of houses, known as horizontal scaling. You have to decide, do you want one huge machine or many small ones? Why does my site crash? When you have one server, a sudden rush of requests quickly overwhelms it. Notice how the incoming traffic turns red as the system struggles to keep up. To handle this, you need a load balancer, a traffic controller that acts as a front door to your system. Instead of sending everyone to one place, it distributes requests across several servers, like server A, B, and C. This prevents any single point of failure. You manage the workload using a load ratio, which is just your total traffic volume divided by the number of active nodes. By spreading the work equally, you keep every server at a healthy 100 units. To measure performance, you look at average latency, calculated as the total response time over the number of requests. Lower latency means your users get their data faster. If one server becomes full, your balancer identifies the strain and intelligently reroutes new traffic to an empty server, ensuring your site stays fast and reliable. How do you store data for millions of people without your server crashing? Sometimes you simply have too much data to handle. Imagine your entire database is one big container holding all your information. When your traffic grows, that single database gets overwhelmed. Think of it like an encyclopedia on a single desk. If too many people try to look up information at the same time, they all crowd around that one spot and nothing gets done. This is where sharding comes in. Sharding is the process of splitting your data into smaller chunks and spreading them across multiple servers. Now, instead of one giant book, you have several specialized volumes. This makes it much faster for you to serve information. But what if one server fails? You use replication. Replication creates exact copies of your data on different machines, ensuring that if one goes down, you have backups ready. You can calculate your total read capacity by adding your primary source to the number of replicas you maintain. To know exactly where each piece of data belongs, you use a sharding key. This formula uses the modulo operator, represented by the percent sign, to take your data hash and distribute it evenly across your available shards. Just remember to scale smart, not hard.
Why does your app feel slow sometimes? Imagine a car traveling down a highway. As the car moves from start to finish, the time it takes represents latency. Latency is simply the speed of one single car moving through the system. Now, think about a toll booth. When you have many cars trying to pass through that same point, you are dealing with throughput. Throughput measures how many requests you can handle in a specific window of time. To calculate these, remember that latency is the end time minus the start time, while throughput is the total number of requests divided by that total time. When you look at a single request, that delay is your latency. But when you look at a box full of many requests hitting your system at once, that is your throughput. It's the difference between feeling like you are waiting in line and feeling like the entire entrance is completely overwhelmed. Is your app fast? When you look at your dashboard, you likely see a scatter plot of your response times. The green dots show most requests finishing quickly, while the few red dots represent the slower requests. If you calculate the average response time, you get a single number that sits right in the middle of all those fast requests. Wait, why is my app still laggy? Notice how the average completely ignores those few slow red dots on the far right. This is where the 95th percentile, or P95, comes in. The P95 is the response time value where 95% of all your requests are faster. When you look at the P95 line, it captures the threshold of the long tail, which is the small set of requests that take significantly longer than the rest. The average hides the truth. P95 reveals the experience.
Why do your requests queue up? When you send data into a shop, the arrival rate, shown here as lambda, determines how fast customers arrive. Watch as they form a queue outside. Inside, the barista represents your service time, or W, which is how long it takes to process each individual request. Little's law states that the queue length, L, is simply the product of your arrival rate and the average wait time for each request. If your service speed stays constant, then as you get more arrivals, your queue will inevitably grow to compensate for the traffic. Look at this graph showing the relationship between arrivals and queue length. Notice that as the arrival rate increases, the curve begins to spike sharply. That point is your bottleneck, where the incoming traffic exceeds your maximum service capacity. To keep things running smoothly, you must always match your system capacity to your incoming demand.
How do you store data effectively for your application? Imagine you have two distinct choices for managing information. Think of SQL databases like a formal filing cabinet where you organize everything in precise slots. This is structured data, perfect for when accuracy matters most. On the other hand, you have NoSQL, which acts like a flexible storage bin for all kinds of varied shapes and sizes, giving you more creative freedom. For that filing cabinet, you rely on ACID, a set of rules ensuring strict reliability, so your data is always consistent and secure. Conversely, the flexible bin follows base principles, prioritizing speed and massive scale over immediate perfection. As your needs shift, you might move along this spectrum, from highly structured and predictable relationships to more complex and unpredictable ones. Ultimately, you are choosing between the rigid, organized nature of a cabinet or the versatile and expandable capacity of a bin. Is your database too slow? When you send a write request from your application to a database, you are essentially asking it to commit new information to disk. If your performance lags during this process, it often comes down to your read and write ratio. This is simply the frequency of data retrievals versus the frequency of data updates. Think of a write-heavy workload like a narrow turnstile where only one person can pass at a time. It requires a specific, streamlined structure. In contrast, a read-heavy workload is like a complex intersection where many users need to navigate different paths at the same time to grab information. Because these patterns differ, you choose different tools. A document store is often optimized for quick writes, while a relational database excels at managing complex reads. The secret is to match your database structure to your actual traffic. Why can you never have a perfectly reliable database? You start with two servers, A and B, connected by a network that allows them to share information constantly. Watch what happens when you send a data packet from server A toward server B. Suddenly, the connection snaps. When two servers lose their link and cannot communicate, you call this a network partition. It is a fundamental roadblock in computing. Think of it like a three-legged stool, representing consistency, availability, and partition tolerance. If you remove the consistency leg, where everyone must see the exact same data at the same time, the stool wobbles. If you pull out availability, the guarantee that your app never fails to respond, it collapses again. Remove partition tolerance, which is the system's ability to survive that broken network link, and the stool falls once more. In the world of distributed systems, you cannot have all three at once. That is the CAP theorem in a nutshell. You usually pick two. You might choose CP for strict data accuracy or AP for constant uptime, but you cannot have CA without risking total failure during a network break. When that partition happens, you as the architect are forced to choose. Do you prioritize showing your user the most current, fresh data, even if the service might pause? Or do you keep the system running and available, even if the information might be slightly outdated? That is the trade-off you face. Why is your app slow sometimes? Think of your computer as an office. You have a desk where you keep the files you are working on right now, and an archive room down the hall for everything else. Your desk is like RAM, your computer's short-term memory. It is lightning fast, letting you grab files in just 100 nanoseconds. Because it is so close, you can swap between projects constantly without any delay. But when you need something from the archive, which is like your SSD or long-term storage, it takes much longer. Accessing the archive takes 100,000 nanoseconds, making it thousands of times slower than your desk. This latency is why fetching data from your hard drive or over the network always slows you down. We call items you use often hot data, and they stay right on your desk where you can reach them instantly. Items you rarely use are cold data, and they get tucked away in the archives. A cache is simply the practice of keeping your most important data on the desk so you do not have to walk to the archive. Faster access to your data means a much happier user. How do you make sure your app is not showing stale, old data? Think of your cache like a carton of milk in your fridge. Just like that milk, your data has a shelf life or a best before date. If you keep it too long, it goes bad. When your application pulls data from the database into a cache, you are essentially creating a local, temporary copy to speed up access. But how do you balance freshness? It is a trade-off between the accuracy of your information and the latency, or the time it takes to retrieve it. One common solution is a time to live, or TTL timer. This is the maximum time allowed for a cached item to exist before it is considered expired. Once that timer hits 0, your system invalidates the data, forcing a fresh update. Another approach is a write-through strategy, where every time you update your data, you send that update to both the cache and the database at the exact same time. This keeps them perfectly in sync. Alternatively, you might choose Write Back, where you update the cache immediately but perform a lazy synchronization to the database later on to save resources. Ultimately, your choice boils down to a classic engineering trade-off between maintaining perfect data consistency and achieving maximum speed. Your memory is full, so what goes? Think of your cache, a high-speed storage area, as a limited workspace. When you try to add new data, like this item D, it bumps against the wall because there is simply no space left. To make room, you need an eviction policy. Visualize your items in a revolving door. As you rotate the door, you can identify the item that has been sitting there the longest, which is our candidate for removal. By highlighting and evicting the least recently used item, you clear a perfect spot to insert your new data immediately. This process helps you maintain a high hit rate, which is the ratio of successful data lookups versus total requests. The cycle is simple. Find the oldest item, evict it, and insert your new data to keep your system efficient. Ultimately, the best strategy is to always keep what you use the most.
What if your server fails? Here, you can see a standard application setup. Your data flows from the database to your API and then out to the user interface. If that middle API layer goes down, your entire system goes offline immediately. Think of it like a bridge held up by one single pillar. If that pillar collapses, your data cannot get across. But what happens if you add redundancy? By adding extra pillars to support your bridge, you ensure that if one fails, your data keeps moving safely across the others. To measure this, engineers use an availability formula. It compares the mean time between failures, or how long things run smoothly, against the mean time to repair, or how quickly you can get a system back up. Reliability is also calculated by looking at the number of backups you have, labeled here as N. The more independent backups you have, the less likely you are to experience a total outage. Ultimately, you must add backups to stop total collapse.
Why does your whole application crash when one part fails? Imagine you are running an online store where a checkout service communicates with a payment gateway. When that payment service goes down, a cascading failure occurs. The error spreads back, dragging your entire checkout system down with it. You need a better way to organize these connections, using a fuse box, which keeps services isolated. Graceful degradation is the strategy of keeping essential parts running even when others fail. Notice how we disconnect only the broken payment service, while checkout and inventory remain online. To manage this safely, you calculate a timeout threshold, which accounts for the latency buffer and network jitter. A circuit breaker acts as a safety switch that snaps shut when a service takes too long to respond, preventing the error from spreading. Think of this failure state as the current state minus the broken functionality. By isolating the problem, you allow your checkout and inventory to keep working, effectively bypassing the failed payment component so your customers can keep shopping.
What if your app could fix itself while you slept? Imagine your user dashboard, where a request flows through the system perfectly. But what if things go wrong? When a server crashes, you cannot be there to manually patch it yourself. Instead, your infrastructure needs self-healing. Think of this like a mesh where one piece breaks and the neighboring parts automatically replicate to fill the gap. To manage this, you use health checks, which are quick probes that run far more often than your recovery time objective, or RTO, which is the maximum time you can afford for the system to be down. As traffic grows, your load metric climbs toward a capacity limit, triggering the creation of a new instance automatically. When a node fails, your system detects the error and instantly reroutes traffic to a healthy, ready node. Finally, you get to maintain a steady state with an active shield protecting your dashboard around the clock. Why should you trust your internal network? Imagine your company data lives inside a large building with a single guard at the front door. You have services running inside, but once the guard lets a request through, everything inside the building is treated as safe. Notice how Service A can talk directly to Service B without any secondary checks. That is dangerous because if an intruder gets past the guard, they can move anywhere. You need a better way. Instead of one perimeter, imagine every internal interaction requires passing through a checkpoint. When Service A sends a request to Service B, it must provide an identity, which is a combination of its service ID and a cryptographic token. That token is essentially a digital key that proves exactly who the sender is. Once that is verified, the checkpoint checks a specific policy to see if this service is allowed to access that resource. Now, apply this to every connection between your services. By placing a checkpoint on every single line of communication, you follow the principle of never trust, always verify. Requests must prove themselves at every hop, ensuring that even if one service is compromised, the attacker cannot freely move through your system. Verify every request.
How do you know who is on the other end of your digital connection? When Service A talks to Service B without protection, you are exposed to an unsafe channel that anyone can compromise. To fix this, think of your services like two people meeting in a secure facility. By wearing identification badges, they can perform a mutual handshake where they both check each other's IDs before talking. Once they trust one another, they set up a secure pipe for their data. These yellow packets represent your information, safely sliding through a protected connection. This process combines a standard TLS handshake with digital certificates for both the server and the client to verify their identities. Because this tunnel is fully encrypted, even a malicious hacker trying to snoop on your traffic will find nothing but noise. This is the power of mutual TLS, or mTLS, which creates trust in both directions to keep your communication private and secure. Who gets access to what? Imagine Alice tries to send a request to your application. When she reaches the front door, she finds it locked tight. Because your app doesn't recognize her permissions, she's denied access. To fix this, you can introduce a policy engine. This component acts as a central rulebook for your system. It calculates a final decision by combining the user input, your security policies, and any relevant data. When your application receives a request, it simply passes the details to this engine. The engine checks the rules and sends back an authorization result. If everything looks good, it returns an allow signal, and you can safely open the door. Centralize your security logic.
Is your website struggling under a sudden surge in traffic? You start with a single server, which has a fixed capacity defined by its hardware limits. You might try to fix this by upgrading that server to be more powerful. But why add more power if one just gets bigger? Eventually, that single machine will reach its limit and crash completely. Instead, you can use multiple nodes, which are individual servers working together. By spreading the load across several nodes, your total capacity becomes the number of nodes multiplied by the capacity of each one. Think of this like choosing between building one massive skyscraper, which we call vertical scaling, or building a neighborhood of houses, known as horizontal scaling. You have to decide, do you want one huge machine or many small ones? Why does my site crash? When you have one server, a sudden rush of requests quickly overwhelms it. Notice how the incoming traffic turns red as the system struggles to keep up. To handle this, you need a load balancer, a traffic controller that acts as a front door to your system. Instead of sending everyone to one place, it distributes requests across several servers, like server A, B, and C. This prevents any single point of failure. You manage the workload using a load ratio, which is just your total traffic volume divided by the number of active nodes. By spreading the work equally, you keep every server at a healthy 100 units. To measure performance, you look at average latency, calculated as the total response time over the number of requests. Lower latency means your users get their data faster. If one server becomes full, your balancer identifies the strain and intelligently reroutes new traffic to an empty server, ensuring your site stays fast and reliable. How do you store data for millions of people without your server crashing? Sometimes you simply have too much data to handle. Imagine your entire database is one big container holding all your information. When your traffic grows, that single database gets overwhelmed. Think of it like an encyclopedia on a single desk. If too many people try to look up information at the same time, they all crowd around that one spot and nothing gets done. This is where sharding comes in. Sharding is the process of splitting your data into smaller chunks and spreading them across multiple servers. Now, instead of one giant book, you have several specialized volumes. This makes it much faster for you to serve information. But what if one server fails? You use replication. Replication creates exact copies of your data on different machines, ensuring that if one goes down, you have backups ready. You can calculate your total read capacity by adding your primary source to the number of replicas you maintain. To know exactly where each piece of data belongs, you use a sharding key. This formula uses the modulo operator, represented by the percent sign, to take your data hash and distribute it evenly across your available shards. Just remember to scale smart, not hard.